Now let us study about second part of ray optics, wherein we are going to study about important points in refraction at spherical surface, refraction in thin lens, lens formula, power of lens, combination of thin lens, prism, simple microscope, compound microscope and telescope. This will be followed by practice questions. Now let us derive the formula for refraction at a spherical surface. Here angle I is the exterior angle in triangle NOC, and as we know, exterior angle equal to sum of angles of two opposite vertices. Angle I equal to angle NOC plus angle NCO. Thus tan I can be written as Mn by OM. How we got Mn by OM? Mn by OM is nothing but tan of angle NOC, and Mn by Cm is nothing but tan of angle NCO. Thus tan I equal to Mn by OM plus Mn by Cm. Similarly, angle R equal to angle NCM minus angle NIM. How did we get angle R equal to angle NCM minus angle NIM? Because angle NCM is the exterior angle here for the triangle NCI. Now angle NCM is equal to angle R plus angle NIM. Thus angle R can be written as angle R equal to angle NCM minus angle NIM. Now taking tan for all these angles, we get tan R equal to Mn by Cm minus Mn by Mi. By Snell's law, sin I by sin R equal to N2 by N1, or we can write it as N1I equal to N2R. How did we get I and R? Because we are substituting I in place of sin I for small angles and R in place of sin R. Also, this I can be substituted by tan I and R can be substituted by tan R if the angle is small. Thus, N1I equal to N2R becomes N1 into Mn by OM plus Mn by Cm equal to N2 into Mn by Cm minus Mn by Mi. On cancelling the like terms and introducing the optical terminologies like U, V, R, we get N2 minus N1 by R equal to N2 by V minus N1 by U. This is the equation for refraction at a spherical surface. From this equation, we will derive other equations relevant to thin lenses. Let us derive lens maker's formula. Let us start with the equation N2 minus N1 by R equal to N2 by V minus N1 by U that we have derived in the previous slide for refraction in a spherical surface. Let us use a convex lens for our derivation purpose. At interface ABC, equation 1 can be written as N2 minus N1 by R1 equal to N2 by V plus N1 by U. Here R1 is positive, U is negative and V is positive. That is, U is measured from the left side of the lens. However, at interface ADC, R2 is negative, U dash is negative. U dash is the object for the interface ADC, object length for interface ADC. And in this case, V is also negative, because the interface ADC, it serves as a concave mirror. You can equate this similar to a concave mirror. Thus R2 is measured, or U dash is measured and V is measured from the left side of this mirror. Further, U dash can be taken as V because the image of ABC serves as object for ADC. Also, U dash is negative because its distance is measured against the light. That is what we have discussed already. If you think of ADC as a concave mirror, you will understand that U dash is negative. Adding these two equations, that is equation of interface ABC and interface ADC, we get N2 minus N1 into 1 by R1 minus 1 by R2 is equal to N1 by U plus N1 by V. If the object is placed at infinity, then object distance U is at infinity and V is equal to F. That is, the image is formed at the focus. Thus, the above equation can be rewritten as N2 minus N1 into 1 by R1 minus 1 by R2 equal to N1 by F. On rearranging, we get 1 by F equal to N21 minus 1 into 1 by R1 minus 1 by R2. For concave lens, R1 is taken as negative and R2 is taken as positive. From the earlier discussions, we know N2 minus N1 into 1 by R1 minus 1 by R2 is equal to N1 by U plus N1 by V. Also, if the object is placed at infinity, U is equal to infinity and V equal to F. Thus, we get N2 minus N1 into 1 by R1 minus 1 by R2 equal to N1 by F, which is equation number 3. From equation 2 and equation 3, we get N1 by F equal to N1 by U plus N1 by V. Because LHS of both these equations are equal, thus we are equating the RHS of these equations. For a thin lens combination, U is negative and V is positive. Thus, N1 by F equal to minus N1 by U plus N1 by V. Hence, we get 1 by F equal to 1 by V minus 1 by U, which is lens maker's formula. This is applicable for both concave and convex lenses. Now, let us understand some of the important formulas. The first one is about power of lens. Power of lens P is given by 1 by F, reciprocal of the focal length, and its unit is diopter. Power of lens is positive for converging lens, that is convex lens, and it is negative. Power of lens is positive for converging lens, that is for convex lens, and negative for diverging lens, that is for concave lens. Now, let us understand combination of thin lenses. In case of combination of thin lenses, 1 by F equal to 1 by F1 plus 1 by F2 up to 1 by Fn. Also, power is equal to sum of all individual powers of the lenses, and magnification equal to product of individual magnification of the lenses. Now, let us look at some of the important concepts in prism. In prism, angle of prism A is given by R1 plus R2. And angle of deviation delta is nothing but sum of angles of incidence and angle of emergence minus angle of prism, that is I plus E minus A. At minimum deviation position dm, I is equal to E and R1 equal to R2. In such a case, dm equal to N21 minus 1 into A. And let us understand that thin prisms do not deviate light much. Now, let us understand magnification in different optical instruments. In case of simple microscope, magnifying power m is given by m equal to 1 plus d by f, where d is the least distance of distinct vision, which is equal to 25 centimeter, and f is the focal length of convex lens. For image at infinity, m is equal to d by f. For compound microscope, magnification is given by magnification of eyepiece into magnification of objective. Thus, m is equal to LD by FO FE, where F0 or FO is nothing but focal length of the objective, and FE is the focal length of the eyepiece, and L is the distance between the focal points. For a telescope, magnification is given by m equal to beta by alpha, where beta is the angle subtended at the eye by the image, and alpha is the angle subtended at the eye by the object. Now, let us get on with practice questions. Question number 1. How does the angle of minimum deviation of a glass prism of refractive index 1.5 change if it is immersed in a liquid of refractive index 1.3? The answer is, Refractive index is given by sine of a plus d by 2 divided by sine a by 2. And refractive index of prism in air is 1.5 and refractive index of prism in liquid is 1.5 divided by 1.3, which is equal to 1.15. Thus, we see that refractive index of prism in air is greater than refractive index of prism in liquid. Thus, angle of minimum deviation decreases. Question number 2. For the same value of angle of incidence, the angle of refraction in three media are 15 degree, 25 degree and 35 degree respectively. In which media would the velocity of light be minimum? We know refractive index equal to sin I by sin r, which is equal to velocity of light in vacuum by velocity of light in medium. So angle of refraction is directly proportional to velocity of, since sin 15 degree is less than sin 25 degree, which is less than sin 35 degree, the velocity of light in the medium where theta equal to 15 degree is lesser than that in 25 degree than that in 35 degree. Question number 3. An astronomical telescope uses two lenses of power 10 diopter and 1 diopter. What is its magnifying power in normal adjustment? The magnifying power of astronomical telescope, it is given by minus f0 by fe, which is equal to minus pe by po, because power is equal to 1 by f. Thus magnification is minus 10. Question number 4. Why is it that the objective and eyepiece of a compound microscope have short focal lengths? The answer is, the objective and eyepiece of a compound microscope should have shorter focal length to have greater magnifying power, as magnifying power of a compound microscope is given by m equal to minus L by f0 1 plus d by fe, where L is length of the microscope tube and d is least distance of distinct vision. Question number 5. How will the position and intensity of the image be affected? The lower half of the mirror's reflecting surface is painted black. The answer is, the position of the image will remain the same as there is no shift in the position of the mirror. Intensity of the image will decrease since the amount of light incident on the mirror will be reduced. Question number 6. Two convex lenses of same focal length but of aperture A1 and A2 are used as the objective lenses in two astronomical telescopes having identical eyepieces. What is the ratio of their resolving power? Which telescope will you prefer and why? The resolving power is given by R equal to A by 1.22 lambda. Here we can notice that resolving power is directly proportional to aperture. Thus, telescope with larger aperture is preferred. Question number 7. When monochromatic light travels from one medium to another, its wavelength changes but frequency remains the same. Explain. We know frequency is the characteristic of source of light and hence it won't change with the medium. A refractive index is given by speed of light in vacuum by speed of light in medium. Speed in turn can be given as frequency into wavelength. Thus speed of light in vacuum is frequency into wavelength 1 and speed of light in medium is frequency into wavelength 2. Thus frequency cancels out to give us the ratio of wavelengths, wavelength 1 by wavelength 2. Thus wavelength is different in different medium, however frequency remains the same. Question number 8. The given figure shows an equiconvex lens of refractive index 1.50, which is in contact with a liquid layer on top of a plane mirror. A small needle with its tip on the principal axis is moved along the axis until its inverted image is found at the position of the needle. The distance of the needle from the lens is measured to be 45 cm. The liquid is removed and the experiment is repeated. Now the new distance is measured to be 30 cm. What is the refractive index of the liquid?
There are two cases. One is without liquid and another one is with liquid. First, let us discuss case 1, without liquid. Since the image is formed at the object position itself, the object should have been placed at center of curvature itself. Thus, center of curvature r is equal to 30 centimeter and focus equal to r by 2, which is equal to 15 centimeter. And hence, mu or refractive index of the lens is given by 3 by 2, that is center of curvature by focus. Case of case 2, it is a combined system. Here, the focal length of effective combination is 45 centimeter and 1 by Fe is given by 1 by F1 plus 1 by F2. Thus, F2 equal to minus 90 centimeter. Also, 1 by F2 can be given by mu minus 1 into 1 by R1 minus 1 by R2. We know the radius of curvature of the lens is 30 and R2 value is infinity, that is of the plane mirror. Thus, we get minus 1 by 90 equal to mu minus 1 into 1 by 30 minus 0. On solving, we get refractive index of the liquid as 4 by 3.